you know this statement, let xi, I greater than or equal to 1, be IID or V, real valued, let's say. You can say the corresponding result for any Euclidean space valued also. Assume that expectation of mod x1 is finite. Then, that's the hypothesis. Then the sample mean, which is defined to be simply the average of the first n observations, converges to expectation of x1 with probability 1. You know how the proof goes. It's in most standard books in probability theory. It's a very important result, and this is what makes statistics a very useful subject in the real world. When you don't know the coin, if you have a coin in your pocket and somebody claims that it is a fair coin and you don't believe that, then what do? You take the coin out and toss it 100 times and see if the proportion of success is approximately 50. Then you're saying, okay, so what? Then you know this other law. This is a result which appeared around the same time as Kolmogorov's book came out. This came out in the early 30s, Birkoff's ergodic theorem. What does it state? Well, you take a probability space. Sorry?
Can you write a bit bigger?
Oh, bigger. You can't see from there? You better check your eyes. No, I'm not kidding you. I'll write big. Is this big enough? Let T be a mapping from omega to omega, be measurable, and P invariant. What does that mean? That simply says that for every A belonging to B, P of A is the same as P of T inverse of A. The typical T that you have to think of, typical omega that you should think of is the Bernoulli shift case, namely omega to be the infinite sequence space of 0 ones, and T omega would be the shifted one. Then, now I'm not done with this hypothesis. Let F be a mapping from omega to R, be measurable, and integrable, let's say, belonging to L1 of P. That is, integral of mod F dp is finite. So these are all hypotheses that I make. And what is the result? Then you look at f of omega, f of t omega, all the way up to f of tn of omega, tn minus 1, let us say. Divide that by n. Physicists would call that the time average of f, the first n generations, and that would converge to, well, what would it converge to? This is the time average. Birkoff showed it converges, but not to the expectation of f that you would expect in the IID case, but the projection of f on the invariant sigma algebra, expectation of f with respect to the invariant sigma algebra. The conditional expectation of f with respect to script f. Script f is the invariant sigma algebra in B with respect to t. T is the basic transformation on the omega space. Well, it is possible to deduce Kolmogorov's result from Birkoff's ergodic theorem if we can show that the tail sigma algebra is actually has probability 0 or 1 every set. The 0-1 law is satisfied. That takes some work. If you have ever studied a graduate course in probability theory, you would have seen that. But now, let me also, so in principle you can deduce Kolmogorov's theorem from Birkoff's ergodic theorem, provided you show for the IID case, the invariant sigma algebra is trivial. That takes some work. But then there is another law which is proved more recently. Well, let me write it down. Not more recently, let's say this is Etomodi's law. Nazarullah Etomodi was a student of Gopinath Kallianpur at the University of Minnesota, and he proved the following result. And unfortunately, I don't know any way of deducing that result from Birkoff's ergodic theorem. The theorem is the following. You notice that Kolmogorov had a strong hypothesis that Xi be IID. Etomodi just wanted pairwise independence and identically distributed. Let Xi be pairwise independent, there is one hypothesis, and identically distributed, and expectation of mod x1 be finite. Then, the same result. The sample mean converges to the population mean with probability 1. I have no idea of how to deduce that result from Birkoff's ergodic theorem. If some of you can do that, that'll be great. But now, I want to prove an ergodic theorem for stochastic sequences which are not necessarily IID. For example, they could be dependent sequences, such as Markov chains, Markov processes. So, let me give you some examples. Oh, let me give you first a definition. A sequence xn, n greater than or equal to 0, is regenerative. Well, it's an ordinary English word, regeneration. So something that generates itself again and again and again. If, or maybe delayed, we can allow that. If there exists J sequence of random variables such that T0 is 0 with probability 1, T1, 0 is less than T1, less than T2, less than T3. These are integer valued random variables, positive integer valued, such that if you look at the excursion eta j, which is equal to x sub n, n from tj less than or equal to n, less than tj plus 1 minus 1, as well as the length of that interval, tj plus 1 minus tj, j greater than or equal to 1. These excursions, these are random excursions. The duration is random, and the coordinates are also random, but these are IID. In a very complicated space. The space consists of a random number of coordinates, and the coordinates themselves can be values in that underlying state space, whatever that is. So that's the definition of a regenerative sequence of random variables. What are some examples of that? IID sequence, Markov chains, discrete time Markov chains, where you can come back to a starting point again and again. I'm not insisting that the TJs have a finite expectation. Regeneration simply means that you come back to the starting point again and again. If so, you can add the definition. It's a positive regenerative, let us say, if you want to do that, if it's regenerative and the expectation of T1 minus or Tj plus 1 minus Tj is finite for j greater than or equal to 1. They're IID anyway. So, any positive recurrent Markov chain, discrete state space Markov chain would be regenerative. Any Markov chain which happens to be irreducible and recurrent would be regenerative. We distinguish between positive regeneration and ordinary regeneration. Here is one example that in continuous time. Well, what's the definition in continuous time? Let x of t be a stochastic process be a random process. When would you call it regenerative? It is regenerative if exactly the same definition. If you can break it up into IID components. What would be an example of that? What is the simplest example of continuous time stochastic process that if anyone were to ask you? Brownian motion. Standard Brownian motion in one dimension is regenerative. Why? You start from 0, you're sure to hit 1. That proof is not easy. That always you hit 1. From 1 you hit 0. So from 0 you go to 1, and from 1 you go up, come back to 0, and then once you come back to 0, strong marker property prevails, and the process starts all over again. So every Brownian motion, every standard Brownian motion is regenerative. How about Ornstein-Uhlenbeck process? That's also regenerative. It requires some proof. But it's not only regenerative, but it's also positive recurrent. Because the mean time to hit any level has a finite expectation. Whereas in the case of Brownian motion, the mean time to hit level 1 from level 0 is infinite. That requires a martingale argument. So, in fact, let me state a theorem for the Brownian motion case. This was proved by Kallianpur and Herbert Robbins way back more than 50 years ago. So let me state that theorem for you. I believe it was around 1953 or something like that. Let B of t be SBM. I assume that all of you know what SBM means, standard Brownian motion. Let F be integrable with respect to Lebesgue measure on the whole real line. The invariant measure for this process is simply Lebesgue measure. Lebesgue measure is not a proper measure. It's an infinite measure on the real line. Let F be L1. Then you want to compute the integral of F with respect to the Brownian motion. Then you do the following. 0 to t, f of b of u, du. Supposing you did that. Then what would you divide it by so that Birkoff's ergodic theorem kind of holds? Birkoff's ergodic theorem will not hold. The underlying Brownian motion is recurrent but null recurrent. The expected amount of time to come back to a starting point is going to be infinite. It turns out you don't divide by t. If you divide by t, you are done. It will go to 0. But divide by square root of t. And then you want to know what happens to this as t goes to infinity. And they showed that this goes to in distribution. So this is a sequence of random variables, converges in distribution to the integral minus infinity plus infinity f of u du. That's the ordinary integral. I'm assuming f is in L1 with respect to the real Lebesgue measure. So that quantity is well defined. That's what I would like it to go to. But then it goes to a random variable mod z, where mod z is n01. Converges in distribution to that. That random variable, by the way, has a name. It's also called, it's not my phone, is it? Is it my phone or is it this one?
It's your phone interfering with the mic.
Oh, my phone is in the same pocket. I have to get it out. Hang on. Okay. Now it will not make a noise, right? Okay. So this is also called Mittag-Leffler. It's a distribution due to Mittag-Leffler. This is a comparison to this result. Take the Ornstein-Uhlenbeck process and then compute the quantity. So supposing let So theorem, we can write it down. So what do I want to let F to be? F is in L1 of R with respect to Lebesgue measure. Lebesgue measure is the invariant measure. What do I want? The corresponding theorem would be what? I want F to be integrable with respect to the invariant measure for the Ornstein-Uhlenbeck process, which happens to be Gaussian distribution. So let's assume that F is reasonable. F belongs to L1 of pi. Pi, an appropriate Gaussian measure on R. Then you can use the fact that starting from any point, you're guaranteed to hit any other point with probability of 1, and from any other point, you'll come back to the starting point with probability of 1. So it's a strong Markov process, it'll be regenerative, and then the time it takes will have a finite mean because the invariant measure is a probability measure. So now you can say then 0 to t f of x of u du. What should I divide it by? In the previous case, in the Brownian motion case, I had to divide by square root of t, and I can assure you only convergence in distribution. Now what? It turns out that the Brownian Ornstein-Uhlenbeck process is a nice process. So it turns out this divided by square root of t, by t, will converge to integral of f d pi with probability 1 as opposed to convergence in distribution. Yes?
F is just a function.
F is just a real valued function on the real line.
So even this earlier one,
yes.
I just consider F to be an exact inner function.
Well, B is a continuous function.
Yeah, but that it just becomes the occupation line.
No, but is that integrable over the whole real line? I'm assuming F is integrable over the whole real line. So you need that assumption. So your example will not satisfy that. Okay? F should be integrable over the whole real line with respect to Lebesgue measure. And that shows up already. And in fact, there is an interesting question here. What happens to the Ornstein, this Kallianpur Robbins result when this is 0? We don't know. I don't know the answer. Maybe if some of you know, let me know. So that's an open question. All right, so now let me get back to some theorems with respect to what are some examples of stochastic sequences which happen to be regenerative. So theorem. Let Xn be a discrete time, discrete state space, irreducible, recurrent Markov chain. I didn't write down all the terms for you, but I said them all. Then, that's all the hypothesis. Every discrete state space, discrete time, irreducible Markov chain, no matter where it starts, it's going to be regenerative. Then Xn is regenerative. Theorem. If you don't want discrete state space, if you are more satisfied with a non-discrete state space, what will you do? Well, you have to make an assumption. So let Xn be a Markov chain. MC stands for Markov chain. Let Xn be a discrete time, general state space, irreducible, whatever that means, Harris recurrent Markov chain. What does a general state space, discrete time Markov chain recurrent means? In the discrete state space case, starting from any point, you can hit any other point with probability of 1. That's recurrence. So what is recurrence now for a general state space case? Well, this is a topic that was discussed a great deal long ago by a German mathematician by the name Dublin, or Dublin, I don't know how you say it. How do you say it? Dublin or Dublin? Okay, you know, he introduced the notion, he says let Xn be, so let Xn be a Markov chain in some state space S comma script S. Then Xn is called, n greater than or equal to 0, is called Dublin recurrent. With respect to a measure, a sigma finite measure phi on S comma S, if the following takes place. If A belongs to the underlying state space and phi of A is positive, that should guarantee that starting from any place, Xn belongs to A for some n finite, 1 less than or equal to n less than or equal to finite, starting from x not equal to little x, is positive, is 1. It's irreducible if it is positive, it's recurrent if it is 1. And now the claim is the following, so you can expect a corresponding theorem, and that is the following, I will state that. So theorem, let Xn, this is the strong condition. We want phi to be a sigma finite measure so that if any time phi of A is positive, the chain hits that A, that set A with probability 1, starting from any place. That's Dublin's condition. Harris introduced a weaker condition. This is the Ted Harris, who wrote this first book on branching processes in the United States. Let Xn be a Harris irreducible Markov chain, which has the following property, that is, with respect to, with reference measure phi, that is, phi is a sigma finite measure on S comma whatever the state space is, and phi of A positive, where only irreducibility implies P of Xn belonging to A for some n, that is the heating time, x not equal to x, is positive. The probability that the heating time is finite is positive. That's all we are assuming. That's Harris irreducible. Then, using what is known as a C-set lemma, Joseph L. Doob proved something stronger. But then let me state a simple theorem. Let Xn be Harris irreducible with respect to some reference measure and recurrent in the following sense. If the following, that is, phi of A positive implies Px of Xn belonging to A for some n greater than or equal to 1 is equal to 1. All right, so, this is a hypothesis. Then Xn is regenerative. So the idea of regeneration of a sequence of random variables not only applies to classical IID sequences, but much more general, Markov chains in discrete time, discrete state space, continuous states or general state space in discrete time. And I asked, I think Vivek, a question the other day. For Brownian motion, we have this result of Kallianpur and Robbins. For Ernst and Uhlenbeck, you don't need to divide by square root of t, but you divide by t itself. And I suspect the following is true. Take any general diffusion which admits an invariant, finite invariant measure. And so long as it is irreducible in a suitable sense, it's going to be strongly regenerative, positive recurrent, and the time average, 1 over t, 0 to t, f of x of u du, is going to converge. That needs to be written down, but it has not been written down. Let me see, what time do I have? How much time do I have? Oh, I have plenty of time. How much time? Okay, very good. So let me pose some problems for you. Have you heard of what is called MCMC? MCMC is a statistical technique. Markov chain Monte Carlo. And unfortunately, it gets terribly misused by statisticians. They have no clue that certain measures, underlying measures, are not even finite. They will use that. One such example is the following. If I assume that I have a sample x1, x2, xn, or IID normal, with some mean mu and some variance 1, let us say. Then if I want to estimate mu, the sample mean will do the job. But here is where the statisticians come in. They wear now the hat of Bayesians. They will assume that I don't know what mu is, and I'll put a measure on the real line. And what measure? They know only one measure, Lebesgue measure. Lebesgue measure on the real line is not a probability measure. So it cannot be a proper prior. So remember, a prior, in Bayes' theorem, you assume mu has a probability distribution. And then you want to look at the posterior distribution of this probability distribution given the data. And then you want to estimate certain functions connected, certain integrals with respect to the posterior distribution. And then you use MCMC. If this measure mu is supposed to be having Lebesgue measure on RBR. If this is your prior, what's your posterior? Posterior is the distribution of the parameter mu given the values x1, x2, xn. If the prior is improper, there is no guarantee that the posterior is going to be proper. So in particular, so if you assume, so here is a standard problem in what's called MCMC. Let x1, x2, xn be IID according to some measure mu, some measure p, let us say. Let p be chosen according to some prior pi on the space of all pressure, space of probability distributions. On the underlying space, let it be a p on some space s comma script s. On s comma s. So if you like, you can think of s to be the real line, script s to be the Borel sigma algebra, if you like. So pi is a probability measure on the space of probability measures, and then having seen the data x1, x2, xn, having seen the data, compute the posterior. Pi tilde, let us say. And then what do? Then the statisticians want to compute or estimate some integrals with respect to this posterior. Pi tilde on the space of probability distributions. Probability measures on S, script S. Then, here is a problem. Estimate some integrals with respect to, say, g of p pi tilde dp. Pi tilde depends on your data. This is a problem that the statisticians want to talk about. But the problem here is the following. This pi tilde is not guaranteed to be proper. So what would they do? They prescribe the following rule, which they don't justify. Is it generate? So here is the MCMC says generate y1, y2, yn is a Markov chain in some suitable fashion. For example, they would think of Markov chains coming from so-called measure and things like that. Some Markov chain with state space, the space of probability measures, space being the space of probability measures on S, S, and let F be a function, a real valued function on that space, and then compute f of yi, I equal to 1 to n or 1 over n. This would be your estimate, they claim. But this estimate will work so long as the yi sequence is appropriately irreducible and ergodic and has an invariant measure given to be what you attempted as your posterior measure. But if your posterior measure is improper, then you are doomed. This guy will go to 0. So much of the computations that you see in Bayesian statistics, you have to have a serious doubt. When is this true? Because very often they assume that the prior is not proper. Like in the case of Lebesgue, normal distribution, you're all familiar with normal distribution. The normal mean is not known, so they put improper prior on that. Uniform distribution on the whole real line. That makes no sense. So that's the problem. However, if you go back to, if you get away from that, so here is a very simple question. Let Aj, j greater than or equal to 1, be a sequence of real numbers. Suppose you know that Aj is convergent. J equal to 1 to infinity is convergent. Then find an estimate of summation Aj. That's my quantity. I want to estimate this quantity lambda. I know that the sequence Aj is convergent. You generate some random mechanism and some averaging procedure such that you can estimate this quantity. What would you do? So I don't know what Aj's are. I only know that the Aj's converge, they're in L1, and I want to find out this quantity lambda equal to summation Aj. That's my problem. What will I do? Well, here is one procedure. So do you understand the problem that I'm posing? And the corresponding problem, you can, of course, think in terms of the continuous time. So here is one solution. Be a SSRW on the set of integers 0 plus or minus 1 plus or minus 2 plus or minus 3 and so on.
For your procedure, you can use for individual values of AJ.
Exactly. So if I can run this simple symmetric Markov chain, and I can evaluate my A at the sites that this Markov chain visits, then I'm in business. Then, well, you compute AXJ only at the places where this simple symmetric random walk goes. J equal to 0 to n sub n. Yeah. Now the question is, what should I divide it by? The standard argument is to divide it by n. Don't. You are doomed. If you divide by n, you will go to 0. But what should you divide it by? Divide it by the number of times the random walk comes back to 0, n sub n. If you did that, then you know the proportion of visits to any particular state and divided by the number of visits to that particular 0, this will converge to summation Aj with probability 1. And what is the growth rate of n sub n? You may remember Kallianpur Robbins result that I had square root of t. N sub n, the number of times a random walk, a simple symmetric random walk comes back to the starting point origin is of the order square root of n. So if you divide it by square root of n, unfortunately it will not go to this. It will not go to what you want it to go to, but it will go to that times a random quantity. Because n sub n, the number of times the random walk, simple symmetric random walk, comes back to the starting point is of the rate square root of n, but if I divide by square root of n, it will converge in distribution to a random variable. So this will go to, in distribution, to summation Aj times a random variable. So when you use MCMC, be careful. Make sure that your prior is a proper one. Otherwise, your posterior is going to be improper. In general, I mean, you may luck out. The posterior could still be proper, but you have to verify that. And on the basis of the data that you have, it may be okay for x1, x2, x1000, but then x1, x2 up to x2000, it may not be, because you see new observations. All right, so let me conclude with one basic result. By the way, these results on the, I'm going to call that regenerative sequence Markov chain. And this is due to a colleague of mine at Iowa State. His name is Vivek Roy and Krishna Athreya. This is published in 2014. I don't remember now where it was published. An electronic journal of statistics, that's what it was called. Let me also give you one more example of a sequence that comes up in what is called time series analysis. So let xn, n greater than or equal to 0, be a random autoregressive sequence, i.e. xn plus 1 is going to be rho n times xn plus epsilon n equal to 1 to infinity, where rho n comma epsilon n greater than or equal to 1 or IID. So the question is, under what reasonable conditions will such a sequence behave right? It's a time series. Time series means that something is evolving over time. And so here is the theorem. Let rho n comma epsilon n be IID independent of x naught, the starting value, and assume expectation of log mod rho 1 is negative expectation of log epsilon 1 is finite, plus is finite, then xn is, well, I will, since I talked about regenerative, xn is regenerative. It's not so easy to prove. It takes a while to prove that. So I throw this problem as an open problem. See if we can prove that xn is regenerative with the hypothesis that on an average, the growth rate is negative, less than 1, and then the epsilon, the error rate is finite expectation. And hence, it's distinct, and therefore, therefore, if you take f of xj, j equal to 0 to n, or 1 over, well, it turns out in this case, it's positive regenerative and positive recurrent. By the way, that the xn is a Markov chain is also not so hard to see this. If I tell you what xn is, then xn plus 1 has distribution completely independent of the past. So it's a Markov chain, continuous state space Markov chain, real valued, and it turns out in that space it is going to be what is called Harris irreducible, and so this divided by this will converge to integral of f of x d pi dx, where pi is the invariant measure with probability 1. That's a consequence of the fact that the sequence xn that I generate is going to be regenerative as well as positive recurrent. So these kind of ergodic theorems are available for positive recurrent sequences. Furthermore, x infinity, which is equal to the limit in distribution, limit is or xn tilde, let us say. Xn tilde, remember you can rewrite this xn plus 1 backwards. So xn is equal to rho n minus 1 times xn minus 1 plus epsilon n minus 1. And you keep going down the line, rho n minus 1 times rho n minus 2, xn minus 2 plus epsilon n minus 2 plus epsilon n minus 1. And you can see what is happening in this case. If you keep iterating this, finally you will get epsilon naught, epsilon 1 plus epsilon 1 times epsilon rho 1, epsilon 2 times rho 1, epsilon 2 epsilon 3 times rho 2, no, epsilon 2, epsilon 3 times rho 3, sorry, and so on. So what will happen is this product sequence will have this sequence will have an appropriate convergence result. And so what we can conclude is the following. The sequence will have a continuous distribution. So claim x infinity will be not only real valued random variable, but will have a continuous distribution, will not be a discrete distribution. Will have a continuous distribution. In other words, it will have no atoms. These are all not easy results to prove, and these results, this particular one, is due to two persons from Kaushik Saha and Radhendra Srivastava and myself, and they are IIT Madras, IIT Mumbai. This is just now being completed, 2017. This one, 2014, as I mentioned already. So, getting back to the basics, you have a sequence of random variables. If they are already IID, you are in great shape. The law of large numbers holds. If they are not already IID, if they are even Markovian, appropriately Markovian, but so long as they keep coming back to a starting point again and again, you are in business. In general, the law of large numbers holds anytime you have an experiment that can be repeated. This is what I learned way back in ISI, Kolkata, and that's a good lesson. All of statistics involves repetition of experiments. And unless you can prove an average result, you cannot make use of what you have learned. So averaging process helps not only in the IID case, but also in the regenerative case, such as even in the Brownian motion case, which is terribly non-recurrent. See, you see that if you're willing to divide by square root of t, it converges in distribution to this quantity, which is deterministic, as well as times this. So you can, in fact, use what are called ratio limit theorems. Instead of computing the average divided by 1 over square root of t, you can divide it by summation 0, integral 0 to t f g of b of u du. So I have to stop. That's what you indicated. Okay, I'll stop. He is